Welcome everyone. Thanks for joining our call. My name is Maciej Piotrowski. I'm a director responsible for enterprise architecture at Iqvia in Real World Solutions business unit. And my colleague with me.
Hello, my name is Jiri Dobes and head of solutions in Johnson Labs.
And together we'll tell you about an exciting project that we implemented recently. That was about using Spark NLP to de-identify notes that we get from doctors and physicians in German language. We'll start with quickly highlighting what Iqvia really is, what is it that we do, and why it was such an important problem for us. I'll show a number of things we did try out before implementing Spark NLP-based solution. We'll talk about the details. What was it that we actually implemented and what it means for us and how do we plan to move it forward. Hopefully that sounds interesting for everyone. So let me start introducing Iqvia. It's actually a huge company, employs over 70,000 people worldwide. It is the biggest CRO, so we actually do clinical trials. But above all, we are a data company. So what we do for a living is ingesting, curating, processing, and analyzing data. And we do it in a large number of countries. We make the data available for research, for really smart people to do smart stuff with it, but to do regular reporting, data extracts, data sharing as well. What's important is that we really do it at scale. We actually have data for over 1 billion patients globally. And of course, de-identifying the data, keeping the data secure is a key priority for us. And we have a number of solutions to do that, focused on structured data. And we'll be talking about non-structured data in this talk. So as you, of course, are all very much aware of, there's abundance of data in healthcare. There's just a lot of it. Hospitals have it, physicians, government organizations, patients have it. The problem is when we start or want to use it, is their data is very siloed, it's messy, it's local, it's dirty, it's just super difficult to use. So when we want to make this data available for analytics, there's just a number of steps that we need to do so that the data can efficiently be used. And of course, the AI part, analytical part, is hard, but this left-hand side of the picture, so actually bringing the data together and making it fit for analysis is really a super hard challenge, in particular when we want to implement it at scale for large number of countries, large number of local providers, different therapeutic areas. Is just super hard. And in order to tackle this challenge, we have a range of solutions. One of them is EMR Factory, so Electronic Medical Records Factory. It really is a platform that is a data factory. It works as an assembly line, connects to a number of suppliers, data suppliers in our case, and produces analytical ready data as outputs. It's deployed to a number of countries with the focus really right now in Europe. So of course, privacy is a concern outside of Europe as well, but in particular in Europe with GDPR, it really is challenging to use the data efficiently and at the time to make sure that it's compliant with all the regulations and the rules. Okay, but we process our EMR data, we have data factory. How is it relevant for NLP? Well, of course, apart from really the structured healthcare information, a lot of it is unstructured. Like you see here on a diagram, a lot of information comes as doctor notes. And if we want to make something like this available for AI or analysis, well, we need to normalize it, right? So we need to translate or map descriptions into something that's more standard, so that someone might use T2D, someone else types in type 2 diabetes. We need to map it to a standardized diabetes type 2 SNOMED code. That's a major concern for us and for many people doing analytics on unstructured healthcare data. But surprisingly, that's not exactly what this solution is about. It plays in the same step, but it's not exactly this. What we are talking about here differs in two aspects. A, we are not really talking about very nice full doctor notes and documents that have beginning and an end and dot and a comma in the middle, and usually we'll be showing more examples later. We are really talking about snippets of text that are created somewhere when physicians use EMR systems, and we need to extract information like diagnosis, posology, product descriptions out of them. And they can look like this. So if you look at it, it's even difficult for a human to make out what that really means. And in particular, to identify if it contains sensitive information, if it contains PII information or doesn't. If you look at the really PHI record and the false positive, it's not immediately obvious which one it is, even for a human, yet alone for a machine. Another complexity is, as you see, that's an example for prescription. Well, for diagnosis records, again, similar snippets of text, but slightly different. And if you look at the posology example, again, similar but different. As you see, nowhere full elegant text, but sometimes capital letters, sometimes not different characteristics of the data. So it's a hard problem and fairly unique to tackle with NLP technology. But you might ask, why do we care in the first place? Yeah, there's PII in the text. Is it really such big of a problem? Well, to us, it is. If we are GDPR compliant, and if we want to comply to all the privacy regulations, we are very limited in how we can use the data when it contains sensitive information. And actually, a lot of data, even our snippets of text, a lot of this data contains sensitive information. If you look at the right-hand side column here with percentages, if you look, it's almost 1/3 of the data potentially contains PI information. That means if we need to be very strict on how we use it, well, we are in a way losing or not benefiting from almost 1/3 of the data that we have. That clearly is a problem, and that's the hidden treasure that we would like to unlock with efficiently removing the sensitive information and still being able to benefit from the full set of data that we so laboriously gather, ingest, and curate. Before we move to the how we used NLP and what we solve for, I would like to introduce just one more concept. And that's a concept, it's what we call bridging. Remember, I showed you how we want to translate or normalize strings like T2D into SNOMED code for type 2 diabetes. The process of going from something irregular, non-standardized into normalized, we called it bridging. And it really is a mix of people that do the work and technology and algorithms that help us do that. And of course, we implemented a number of systems and solutions and processes that help us. I'll just show you an example of such a system that people, algorithms run, they figure out what they can figure out. There's always something left that algorithms can't handle efficiently, or there's manual revision process to it. So that's what our bridgers do. They use interface like this one, where the purple codes are the descriptions, the way we get it from the suppliers, and they try to bridge it to the reference data showed in blue columns. And that's in the context of this process that we are implementing our solution. And I think you'll understand by the end of the talk why it's so relevant. Okay, so let me show the situation now and the situation after we use Spark NLP. Right now, it's fairly straightforward. We get the data from the supplier, we process the data, and we have our bridging that does, well, the bridging itself, plus it handles identification of PII information. so that we never disclose it. So it's like I said, mix of algorithms and people doing the work, all mixed somewhere here within our system. That's not good. We would like the bridgers to focus on bridging. So the desired state would be, well, let's split it. Let's focus the bridging effort and everything that's happening on the data warehouse side really on what it should be doing. So really standardizing the values. And let's handle all the free text, all the sensitive information. Let's handle it in a dedicated environment. It has a number of benefits, the biggest being, well, it means then that we don't have any sensitive information here in our data warehouse, so the number of constraints and the restrictions is much smaller. We are much more flexible in how we can process, expose, and use the data. So that would be a brilliant thing to have. So the only caveat is that we need a technical solution that allows us to identify personal information in free text. Okay, so how do we go about that? We started with a POC. We thought, well, there are so many tools, open source tools, great tools also within Iqvia already that can do named entity recognition and all this stuff. Surely we can just use it and it would work for us. We did a POC with a number of solutions like this, and we have drawn two conclusions. The first one, well, the results are quite promising. We probably could use it. Using these libraries and solutions, we achieved precision and recall that were promising. But none of them were really perfect. It seems that solutions built for other use cases or generic use cases, well, fairly quickly reaching the limit, we're dealing with the data the way we had it. Remember this weird text snippet with all the capital letters and oral sentences and all that stuff. So that's when we decided we would run this second POC with Johnson Labs, with experts who specialize in handling this type of scenarios. And the results were brilliant. Not only did we manage to get better quality of our identification, so better precision, better recall, but also technically we were able to run the inference much faster. So it's using open source on a small batch of data. It would be a few minutes. It went down to minute and a half with Johnson Lab with no particular tuning. So great stuff. How did we go about implementing it? Well, that's the part where I would like to hand over to Jiri, who will walk you through it.
Okay, hello. Thank you, Maciej. Can we go to the next slide, please? Right, so first, let me quickly summarize what is Spark NLP for healthcare. So we did it with Spark NLP for healthcare. Spark NLP is the most widely used NLP library in the industry. And Spark NLP for healthcare is the commercial extension. And basically it covers full spectrum of NLP problems, including also the identification. Like example, what it can do, it's shown on the graphics on the right. Can you go please to the next slide? So let me come back to the notes. And there are specific challenges for German language. In German language, you have names, and the names of diseases and locations are all personal names, which of course create specific challenge, which is not so often seen in other language. So let's say in the first bullet point there is Mr. Koch, but also there is Koch called substitute for tuberculosis. In the second one, there is Mr. Wagner, but also there is a surgical technique, which is called Wagner, or Johannes, it can be as a Krankenhaus, which means the hospital, or Steinberg, it can be bone necrosis, or also name in the Germany. Can you go to the next slide? Right. So in order to properly de-identify nodes, we need to follow certain steps. So as a first step, we need to build annotation guidelines where we exactly specify how the de-identification will be performed and what will be marked as a person per PHI and what will not be marked as a PHI. So, for example, for name, you need to have agreement that, for example, doctor's title, or professor, doctor, Mr., will not be marked as a part of a person name. On the second example, on the location, that Krankenhaus, the hospital will not be marked as a location. However, if it is part of the name, it will be like Brandenburg Clinic. It will be marked as a part of location, etc. And it needs to be followed consistently in all the training samples or training data. Next slide, please. As a second step, we took Annotation Lab. Annotation Lab, it's enterprise level annotation tool, which is optimized for annotating high volume of data. And it also runs on air-gapped server, so there is no need for internet. So we took the Annotation Lab and we annotated training samples. For each group, it was roughly 200 nodes, in total 800 nodes, which is, let's say, good size of data set for proof of concept. For the production use, it would be better to have a bit more nodes. Can you go to the next slide, please? Yeah. Then we train the models. I will not cover training of the models in this talk. But this is how we build the inference pipeline. So with the models, then you have the pipeline. Then the pipeline has certain steps. So first is document assembler. It's just changing internal representation of the document. Then we need to detect sentences. So we use a deep learning sentence detector. This is working for multiple languages. Then tokenizer, word embeddings, and then comes a name entity recognition model. This was the model would be trained in the previous step. And then there is a contextual parser. Contextual parser is the annotator which can work as regular expression, but it has extended functionality, wider functionality than just regular expression, and we use it for the detection of IDs like card number, social security number, and also date. Then we merge all the extracted entities coming from name entity recognition model and also from IDs from the contextual parser and date from contextual parser, and we fed it into the identification step. So it is the step where the personal information are removed from the text. And there were several options. Maybe the first and most obvious is just replacing of the names with, let's say, with stars. There are two variants. One is you replace just with stars. The second is you replace only with fixed length. So each name replace, let's say, with 4 stars. There is also another way, which is you take a random name from the dictionary and you replace the personal information from the dictionary. The advantage comparing to masking is that if there is personal information which was not identified by the model or by the pipeline, you will not recognize on the first sight that it stayed there, because it will be the name, while all the other properly identified PHIs, they were changed for some random name. And finally, and it was required by Iqvia, changing the obfuscation, but with the random name with the same number of characters as in the original text. So in this case, William has 7 characters as well as Michael has 7 characters. Can you go to the next slide, please? Okay, and now we have the pipeline and we should measure the results. So there are different ways how to measure results. One is, we call it full chunk. So the area which is identified as a PHI or as a personal information is just compared with the result. And in this case, Robert E. Harris is correctly identified, while ABC Hospital, for example, ABC is missing. So we say that this is not correct, while the name of the person is correct, and we have 50% score. Another way, it's partial chunk per token. Is the chunk is split to different tokens, and then each token is checked if is it correctly identified. And in this case, we have 5 tokens, one of which one was not correctly identified, and we get score 80% forfeits. And this needs to be aligned with the business needs, really, to understand the way how business is interested in the identification of the nodes. Can you go to the next slide, please? Right, and score overall, we got roughly 95%. So if you compare it with the results which was obtained in the first POC, the error dropped to roughly half. And so that was around 90%, this is 95%. And when we reviewed the incorrectly identified PHIs, in most cases, it was they were just corner cases, or it would be up to discussion if this is really personal information, or maybe it's a name of disease or its location because of the type of the nodes that we were de-identifying. You saw that they were just snippets or like very short nodes. So even there was a personal information, it is not always recognizable by a human that it is really personal information. And overall, it follows the pattern that more data we have, the better results it is. And we trained the model like from all the datasets. We merge them. We add the dataset from Johnston Labs and proprietary dataset, and we trained the model. And we did 85% split to train and test. And this is if you calculate micro average, you're in 95%. Can you go to the next slide, please? In similar situation, you can see for the recall. F1, it's more appropriate for the evaluation of the method, while the recall is really the business interest, because you don't want to miss any PHI. Okay, can you go to the one? Right. There were few things which we didn't consider during this POC, and it's planned for the future work. So one piece was treating of the abbreviation of the first names. This we plan to do with a conceptual parser. Then the improve of the confusion of the names versus treatments and versus location. It is also possible to improve with conceptual parser. Then treating of the phone numbers. Phone numbers were identified through name entity recognition model, deep learning name entity recognition model. Then improve the threshold, improve the recall in the expansion of precision. So really optimize on the recall and train models on more data. And the next one is deployment in Iqvia. We will use slide pipelines, which will give low latency and fast API to provide the API and deploy it in Docker. Thank you, and over to Maciej.
Thanks, Jiri. So indeed, what we are, so it seems to be working really well for Germany, and we plan to take it on the road and implement for subsequent countries. The next one in line is France, and the others marked green, shown the map here. All that, keeping in mind that we want to ensure the best possible compliance for our data. I would like to stress that, well, we are processing data as it comes in, but I said we have a lot of data sitting there already. We have our archives and warehouses and data lakes. And that's where we learned that having it in a Spark-based model is just brilliant, because one thing is to have what Jiri showed, API containerized model we can use to score incoming data, but we can then run it on our data lakes and cluster the same models to process historical data, which for us was just a huge thing. So if I were to sum up what we learned here is, first one, not that surprising, that accuracy matters. If you just look at F1 scores, you might not, 91%, 95%, does it really matter that much? Well, it does if you're interested in optimizing recall only. So you need to be really careful looking at your numbers. The speed matters as well, both in terms when you serve the model and you train the model. So the differences I showed earlier versus the open source model, there are actually very significant for us when we have ongoing 24/7, 7 days a week pipelines that are running. Each use case is different. Really, we started with fairly good models used elsewhere in Iqvia in the world. They didn't really work for us that well. So the specific context really matters in this type of solutions. We had a aha moment, really, with what we usually said, that replacing not with stars or asterisks or hashes nor masking, but with other values from dictionary, it actually opens up new possibilities how we can think about ideal recall. It might seem obvious, but for us, it was a game changer when we started doing it this way, because right now, even if one record gets unnoticed, well, there's really no business impact. So that was great stuff. And working with Johnston Labs allowed us to focus on what we do the best. So optimizing, bridging, and doing the pipelines and curation and all that stuff. But it was great to have a partner who not only gives the technology, but understand the processes and the context to make the solution really fit the needs that we have. So we are actually putting it in production right now. So next quarter, by the end of the quarter, it will be live for Germany, and then the subsequent quarter, we are starting rollouts for subsequent countries. So it's been an exciting POC, and hopefully exciting rollouts awaits us. And with that, I would like to thank you for your attention and open up for questions.